Welcome back, Chemistry 30. This is the beginning of the atomic orbitals, representation of orbitals, and electron configuration section for the introduction to chemistry. So what we'll be looking at is, in this video, quantum mechanics and atomic orbitals, electron configurations, and then electron configurations and the periodic table will be the following two videos. So up until this point, we've been looking at, or I guess in grade 9 and grade 10 science, you looked at Bohr diagrams. So for example, oxygen, which has an atomic number of 8. So of course that means we have 8 protons and 8 electrons. So you would have envisioned it like this. You would have envisioned 8 protons in the nucleus. And then this first level or orbit, there'd be 2 electrons, and then 6 following this one. Which means, yes, there'd be 6 valence electrons or 6 outer electrons in these defined orbits. And of course, with the beginning of quantum mechanics, we needed a better model for that, because this doesn't completely describe all elements. It does a not bad job of describing hydrogen, but some of the larger elements, it doesn't do it very well. So that's where the beginning of quantum mechanics and atomic orbitals, not orbits, but orbitals came into play. So what we'll do in this video is we'll look at quantum numbers and relate them to the types of orbitals and recognize the different types of orbital shapes. So first of all, looking at the Bohr model that you have looked at up until this point, of course, grade 9, grade 10 science. The most significant, what's most significant about the Bohr model is that it introduces 2 important ideas that lead to the current model. So electrons exist in certain energy levels, discrete energy levels, which are described by quantum numbers. So yes, we had level number 1. We could call that the n equals 1 region, and then level 2 is n equals 2. So n describes the main level we are at. And energy is involved in the transition of an electron from one level to another. So electrons can be bumped. If I looked at a hydrogen atom, for example, that has 1 electron in this first level, we still have these other levels, and if it were to absorb energy, it could bump up to a higher level. And of course, when it comes back down, it releases energy as well. So that's what the Bohr diagram, the Bohr model helped predict. So unfortunately, the Bohr model did not explain the observations of other atoms besides hydrogen. Rather than electrons being bound to certain orbits, it was found that it's better to discuss the probability of electrons existing in certain regions of space at a given instant. These regions of space are called orbitals and are a result of quantum mechanics, and therefore has led to the quantum mechanical view of a model. So since we can't say precisely where an electron is, we have these regions, and quite often we will be talking about, with approximately 90% of the time, where we will find them in a specific region. Just like in a classroom during the week, at a certain time you may be in a certain classroom. Usually, hopefully better than 90% of the time, but that's how that works. So orbitals and quantum numbers, each orbital has a characteristic shape and energy. For example, the lowest energy orbital in the hydrogen atom has a spherical shape, as we'll see. So we can kind of look at this. This is a 3-dimensional view of an area in space, and you can see each of these dots represents where an electron can be found. So we could say, okay, well, this region here forms a 3-dimensional sphere. That represents where we could possibly find an electron 90% of the time. So it's a region of probability. So note that orbital quantum mechanical model, which describes electrons and probabilities, we kind of envision them as electron clouds or regions in which we find electrons. It's not the same as an orbit, which is kind of that circular region that we have in the Bohr diagram that makes us think about the solar system. The quantum mechanical model does not refer to orbits because the motion of the electron in an atom cannot be precisely determined, which was said by the Heisenberg uncertainty principle. We cannot know exactly where it is. The Bohr model introduced a single quantum number, which we call n, to describe an orbit. The quantum mechanical model uses 4 quantum numbers, n, l, ml, which is a subscript l, and ms, which is a subscript s, which result naturally from the mechanics used to describe an orbital. So the first quantum number, that warrants a different color here. The principal quantum number, which is symbolized as n, can have a positive value, 1, 2, 3, 4. So it's very similar to what we viewed the original Bohr diagram. N equals 1 is a first level, n number equals 2 is a higher level. As n increases, the orbital becomes larger. So you can think this region in the first level is a certain spherical shape. In level 2, there's another sphere that surrounds that sphere, and it's bigger. So you kind of think of the first level would represent a baseball, the second region would be a basketball, and that baseball is inside that basketball. So the electron spends more time kind of in that larger region. So yes, it spends further away from the nucleus. As n increases, n also means the electron has higher energy. So if it's farther away from the nucleus, of course, it's less tightly bound, and there's a large chance that it can be removed. Okay, so n is the main energy level. The second quantum number is the angular momentum quantum number, L, and it can have values of 0 to whatever n is, subtract 1. And it defines the shape. And the general shapes that we talk about, so the lowest value that L can have is 0. And it increases. For example, if n is equal, if I'm looking at the third main level, well, L can have values of 0, 1, and let's see, 3 minus 1, 2. Okay, and we'll be referring to these shapes as an S shape, a P shape, a D shape, and an F shape. And they correspond to L values of 0. So S is represented by 0, P is 1, D is 2, and F is 3. Okay, and in a bit you would have received a sheet that looks like this. I'm not sure if it's the exact same color, but we'll have a summary of all of this on there. All right, so the value for L for a particular orbital is generally designated by letters S, P, D, F, which corresponds to 0, 1, 2, 3. All right, so the shape. The next quantum number is the magnetic quantum number, or ML. And it depends upon whatever L is. So for example, if I'm looking at the L equals 1 region, well, ML can be from -1, 0 to +1, including 0, of course. So it's a range of numbers, as we'll see. And it tells us what the orientation is in space. Is it along the x-axis, the y-axis, the z-axis? Which way is it? And the last quantum number is the spin quantum number, which is denoted as ms. S stands for spin. The two possible values. Now, so we're dealing with integers here, so to separate from other things, we have either a spin in one direction, as you can see here, or a spin in another direction, making a magnetic field. We refer to those as a +½ or a -½ spin. Don't let the fractions confuse you. It's just simply a way to distinguish these numbers from those ones up there. A spinning charge produces a magnetic field. The two oppositely directions for spin therefore produce opposite magnetic fields. So there we go. So there are all of our numbers. And yes, on the bottom of this page, there's a nifty chart there that summarizes all of that. And of course, you will get a copy of that as well. All right, we're almost at the 10-minute mark, so we'll stop that video, and then we'll look at part 2.